Okay, so we're back
Are you recording?
and I'm recording. And I don't know if the shit is actually there, but let's see, black screen. So actually, remember I said this picture is kind of pointless? So actually, this is what I want to show you the lab, and it's actually the next slide. The next slide is how you do it in units. Let's just look at it quickly. I don't expect you to remember all of this, but here is your main. You should be able to understand this program because it's in C. It's in C, which is like C++. And if you have a problem, if you don't understand something, tell me. That's a comment. PID is an integer equals fork. So I made two processes. That's what fork does. Now I check if the PID, we did this in the lab, didn't we? We did a fork, and we checked.
Yeah.
If the PID is less than 0, then it's an error. We didn't do this, actually. This is a very good thing to do. Creating a process is not a blocking function. What does that mean, somebody? Not blocking. It's non-blocking.
Succeed or not succeed.
Exactly. It'll either succeed or not succeed. So therefore, I need to check if PID is less than 0, I did not succeed. It's a possibility that I failed. Printf, standard error, fork fail, return 0, end the program. And now if I didn't get less than 0, then I succeed. So now, if the PID is equal to 0, I'm the child. Else, I'm the parent. Let's go to the else first. Look at what the parent does. Wait, no, he just waits. He waits for what? For the child to finish. Wait is a special command. It means wait for the child to finish. It actually, how does it work though? How does that work? What do you mean wait? We never had a function like that. Wait, is the wait a blocking or non-blocking function? Right. That was a tricky question.
Is it blocking? Because it won't continue until it receives feedback of the child.
Exactly. So therefore,
It is blocking.
it is blocking. Wait is blocking. So a blocking function, just for your information, a blocking function is something you never experienced before in your programming. A blocking function is only capable of being done by the operating system. Right? The operating system can say, this process is blocked. It's not doing anything now, and we're just waiting for something to happen. In other words, there's no flow. We're not going to get to that printf. It's not like it does this function, it does the next function. It stops there. So it's blocking at this wait. And now what's the child doing it simultaneously? It's doing exec. This is a form of exec. It's exec LP. I don't need to explain the whole thing. It's like exec. What does exec do? Exec means you give it a path. It takes a parameter, which is a path, and a name of a function. So the path of the function is ls, bin ls, /bin /ls, and then the name of the function is ls. That's the function I want to run. What is a function? It's not really a function. It's a program that's been compiled, written in C, compiled, and is sitting there on the disk. And I'm saying run that program. Now the way exec works is that when it runs that program, it no longer continues running the child. It just runs that program, and when that program finishes, the child finishes. So it's going to run this ls. The minute it finishes, it will send, the operating system will send a signal, or essentially the child will send a signal, but the operating system is delivering it. The child will send a signal, I finished, and that will wake up the parent with wait. And now you could ask, well, why did I need to create a child if all I want to do is this execl? Just have the parent do the execl. Why create a child and wait? Did somebody answer? Why did I do this? Why did I make a fork? Let me just run exec and run ls, run the function of the command for ls, print out the files in the directory, and then print child complete, and then print I completed. Why create a child?
It can't be in the middle of something else, and to have it stop into ls would mess up whatever trajectory it's on.
Okay, but if you think about it, I did stop. I stopped because I did my wait. In this example, without changing it at all, is there any advantage to it? You're saying if I want to do something while he was doing the exec, I didn't want to do the wait right away. I want to do something else and then do the wait. That's true. As it is now, is there any advantage? Is there anything?
No.
No, there isn't. What is it? Or what? I'll tell you like this. If I would have done it the way I just said, just the parent do the exec, and then I would have printed, I finished with printf. It never would have printed printf, I finished. It never would have done that. Why? No, because the minute I do exec L, I replace my process. Let's understand this. I replace my process with the program that I want to run. I want to run the program ls. ls becomes my process. ls doesn't have any printf I finished in it. So it's just going to run ls. When ls finishes, it finishes. It'll never come back to my program. It'll run the other process, and when the other process is finished, it'll be finished. It will never come back. This way, in other words, essentially it's like I tell the child, go do ls and then kill yourself. You know, that's it. You do that and then you're done. I create a child to do this. If I would do the ls myself with exec, then I would kill myself, then I would die immediately after I finish the exec. And I would never do anything else. This is the way of preserving the father. Because anytime you do exec, you're actually running a different process from the original one. And you never come back to the original process. Therefore, you need to create a child who's like expendable. I mean, nobody's children are expendable. But process children are expendable. Okay, so now we're just, talking about process termination. Obviously, when the process finishes, the resources are deallocated. If you had a child, if you had a file open and the process ended, so the file will be closed. We talked about the weight, output data from the child to the parent. It's possible to send data by the weight also. There's a status variable. I could actually send a small a pointer to the parent. Parent may terminate execution of child process with abort. So I guess the parent can run abort and kill the child in the middle. Now, the interesting question is, what happens if the parent dies before the child dies? So what happens? What do you call a person whose parents died?
Orphan.
An orphan. So the process becomes an orphan process. We call it that. And what happens is, but every process needs a parent. Because there's a function, for example, called get parent ID, get PID, get PPID, parent process ID. So whenever there's an orphan, so there's a nanny who inherits it. And the nanny is the operating system in it. The operating system itself becomes the parent. If what if the child finishes, but the parent never did a wait? The parent just went on running, doing all kinds of stuff, and he never did a wait. Then the child was called a zombie.
Never did a what?
Never did a wait for him. Remember, we saw this example. There was a wait where the parent waited for him. Now,
Parent never waited, or
the parent never did a wait. Never ran that function wait. Never blocked himself. He just continued running, calculating pi to 10 million decimal points. So the child now finished, but he's sort of waiting around in limbo. That's what we call him a zombie. He's half dead. He's dead. He's finished. But he's not fully dead because he's waiting around. Maybe the father will tomorrow do a wait. So I better hang around kind of to indicate some of my data has to stay in the operating system memory in case the father requests, oh, you finished? What was your status when you finished? So there might be a wait coming in the future. So the operating system has to sort of maintain data on any process that finished, but whose parent didn't request the data yet.
Has to maintain the child's data while it's.
Yeah, has to maintain the child's data. And we call that a zombie.
What happens if it never makes a wait? It just is.
If the parent dies, and then the zombie will also die. That's a good question. If there's never a wait, how do you get rid of a zombie? So, right, if the parent dies, the zombie will go away. So if anyone asks you if zombies are real, you tell them yes.
They live inside our computer.
They live inside the computer. All right, so this slide is just to show you that Chrome browser has multi-processes, has multiple threads. Okay, now we're talking about a topic of interprocess communication. It's of course like a history course. We're just learning a lot of concepts, but it'll eventually turn into 9th grade algebra because we're going to start doing things like calculate. Remember I talked about first come, first serve? We're going to start calculating. Okay, what if this process came at this time, and this one came at this time, and this one came at this time? And this one was, who will get, what will the throughput be? How many processes will get through in an hour? A minute. How long will each process wait? What will be the average wait time? That's the question I'd like to ask also. What's the average wait time? How long is the process wait based on the algorithm of schedule? So this is that's like even less than 9th grade now.
Most of the questions on the exam is gonna not be really on this, it's just gonna have.
Oh, we both. It'll be like, since I'm writing these, in the past, it's been like 80% math and 20% this. I'll probably do it. I don't know if I'll do that. I don't know. Maybe I'll do 50%. I will have questions on things like what's on the process. Okay. But I'll also have that. Yeah, my tests, I would say, are hard because they cover a lot of material, not because the questions themselves are that. Like I just finished Unix exam. I was trying to make it easy, but it's 20 questions on a lot of material, and none of the questions, each one question is pretty basic, but you have to learn a lot of stuff. So yeah, you have to know. Okay, so what is interprocess communication? Once we have multiple processes, we want to have a way that they can work together. If they're going to work together, they have to communicate. There has to be data sharing, right? If I calculated pi, at the end of it, I have to give you pi. You have to get that value. Everyone knows that calculating pi is a mathematical puzzle. Pi, we think is 3 point. But Tosfos says that pi is 3, which is more or less right. It's 3.1415, etc., etc., etc. But the point of it in pi is that it never repeats. In other words, there's no series. It's not like 141514. It doesn't repeat itself. It just keeps on being different numbers. And so there's mathematical calculations of how to calculate. But you could set a computer to do calculated pi to a million decimal places. Busy for a long time. So that's why I use it as an example, because there's no actual number. Everything that we say about pi is an approximation. Irrational. Processes within a system may be independent or cooperative, right? So you can have two processes that are independent, or they can work together. Why would I cooperate? I want to share information. Maybe make my program run faster. I don't know if you do a course. There's a course once over at on parallelism, and which discussed which kinds of algorithms actually can be made to run faster, because obviously if I want to calculate 10 numbers, if I do two processes that each calculate 5 numbers, it'll go twice as fast, right? If I have two processors. What if I only have one processor and I divide it into 5 and 5? It's not going to go any faster. In fact, it'll go slow. It'll have to switch back and forth. So you need to, so if I just want, but there are some algorithms that if I want to calculate, so again, if I have two processors and I have, each one gets 5 and 5 numbers to calculate, so it'll go twice as fast. And if I give one processor 10 numbers, that's obvious. But what about this? What about if I have some algorithm that by dividing it between 2, instead of taking 5, it'll take 4. It'll take, it'll go faster. Are there algorithms like that? That by dividing it, I get actual gain. Even assuming I have two processors. I think I have a whole class on that, as I recall. Look that up. Are there algorithms that are speeded up by running in parallel more than the action than the minimum obvious speed up? Okay, cooperating processes need interprocess communication, IPC. two models, shared memory and message passing. So shared memory is that they have a space in memory between the two processes that one can write and one can read, or both can write and both can read, and they can communicate that way. They can send information. I can put the calculation of pi in this shared memory location, like an array. I have an array, but instead of the array being for my process, it's for both of our processes. Obviously, in threads, in multi-threading, you always have shared memory. So it's not much of a, it's obvious in multi-threading that you'll have shared memory. But even in processes, you have a special, the operating system will allow you to create shared memory between processes. If we go back to this example here, what we'll do is we'll say, before the fork, look at this example with the fork. Before the fork, we'll type in create shared memory create as a function. And we'll get that, and then we'll do fork. Now the access to that shared memory will be multiplied, but the shared memory itself will be a single piece of memory. In other words, it won't double the memory that we've created. But the pointer to it, we have two pointers, the father and the son will each have a pointer to that shared memory. In other words, right, like I can't draw on this, but I'll write a function over here. My pointer equals shared memory create of size 100. Now, when I go to this fork, I'll have my pointer, there'll be two my pointers, one by the father and one by the child. The father can write to that pointer and the child can write to that pointer. But the thing they're pointing to, when I said my pointer equals shared memory create of 100 bytes, so that 100 bytes is still 100 bytes. I didn't get 200 bytes. Just like I opened a file. If I did my file pointer equals new file, so the new file is one file. Now I have two pointers to that file. So the fork will create new double variables, but not double resources, like memory or files. So that would be how I would use shared memory. Message passing is usually by a pipe. Let's see. Let's look at this. I didn't explain what a pipe is. I think we're gonna explain what a pipe is. No, we're not. Whatever. We'll stop. We'll see how he explains shared memory. So here, process. Oh, here's the two models. Here is a shared memory. Process A, process B. See, each one has a pointer to the shared memory. See the arrow? That's a pointer. Now, if I'm going to have message sharing, look at this. This is more complicated. If I want to send a message, I'm going to have to use the operating system is going to have to help me here. Because he's going to have to take these messages and say, oh, who you was sent for him, from him to him, so he'll deliver it. Somebody has to be the delivering agent. That will be the operating system, because he knows about the two processes. So you have send and receive functions like send and receive some kind of message. Message passing may be either blocking or non-blocking. Blocking is considered synchronous. So now we're going to equate some terms here. Why is blocking synchronous? Blocking send has the sender block until the message is received. Blocking receive has the receiver block until the message is available. In other words, I say I want to send a message. What would it be if I sent the message in a blocking fashion or a non-blocking fashion? What would that mean? What is the difference?
If it failed, if it wasn't blocked, it would just keep going on as if it may have two plus problems down the line, but.
All right, so I hear you say you're using the definition that I gave before, which is great, except that we're adding a little bit new aspect to it actually. So but very good what you said. But I'll add an aspect to it. The blocking, when we talk about synchronous, when we say a blocking send would mean like this. I send it and I don't do anything until I know it's received. A blocking not send, a non-blocking send would be the sender sends the message and then continues on his merry way without making sure that it received, that it got there. He just sent it. It's like he put Well, you put a letter in the mailbox and you just send it. You don't wait for the reply. You just put it in. That would be a non-blocking. A blocking would be, I don't do anything until I know that you received it. Also receiving. The receiving could be blocking, which means I say, please give me a message. And then I wait until I get the message. What would a non-blocking receive be? Yeah, he would have to get, non-blocking would be, non-blocking receive has the receiver receive a valid message or enough. In other words, I'm basically checking my mailbox, did I get something? And if I didn't, I continue on. As opposed to I stand by the mailbox and wait for the letter to come. I check. Sort of like so why is one called synchronous and one called non-synchronous or asynchronous? Blocking is considered synchronous. Why is that? You're synchronized. Why are you synchronized?
It's like depending on which work you're doing.
Right. You're not right. Exactly. You're doing everything step by step. I'm not advancing. I'm waiting for you. It's like a message. I'm waiting for you to tell me you received, and then I go on. And then, so we're doing it in sync. We're synchronized. I know exactly when you are doing your. I know what your rate of advancement is because it's connected to my rate of advancement. Our rates of advancement are connected to each other. We both advance together. I send you a message and I wait. Now you send, and I wait for you to receive it. Now you received it. Now we go forward. So I don't go forward until you're at the same place as I am. That's called synchronous. Asynchronous would mean I just go on my merry way. I send you a message and I continue on my merry way. It could be I'll finish way before you. It's actually an incorrect usage of the word synchronous. What is the word synchronous? I mean, synchronous in modern English, I guess, means that. What's the technical meaning of synchronous? Well, from Latin. Or from Latin or Greek. Syn is with, and chronos is time. It means with a clock. In architecture, we talk about synchronous. Synchronous means with a clock signal.
Real time.
No, yeah, it could be real time. No, I mean, if you remember architecture, I don't remember we talked about the end of the course with electrical signals up and down. We talked about signals. I don't know, so forget it. But sometimes messages can be passed through the clock stamp, and that would also be called a synchronous message because it has the timestamp. In any case, messages can be synchronous or asynchronous. It just means whether or not we do things together, whether we wait, whether one side waits for the other side to receive before going on. That would be synchronous. Here I send something. Here I'm in an infinite loop. Now notice this send is blocking. You see, if this would not be blocking, this loop would just run a billion times. This is blocking. So it's okay to have this while true infinite loop here because he's going to send one message. Well, actually, wait a second. Oh, he's producing an infinite amount of messages, but this send won't send the next one until the receive is received. I guess. This is a rendezvous. Notice I send. And I'm not going to send another one until this receive returns back. Gives me this send will return some kind of success. Quite like that example. Let's go on. Yeah. Let's go to shared memory. Here's our shared memory open. Remember I said it returns a pointer or some kind of file handle? That's this SM file descriptor. FD stands for file descriptor. So I open the shared memory. Process first create shared memory segment, also used to open an existing segment shared. Set the size of the object I can say the size of it is 4,000 bytes. Now the process could write to the shared memory. F shared memory, write. This is pseudocode. Still pseudocode. You wouldn't write like this. You would write the F. You wouldn't write like this. This is pseudocode. But the point is, I can write to the memory. Yeah, I want to skip this. We'll talk about producer-consumer problems. Socket, we should also talk about. A socket is how the internet works. Every computer can have 64,000 sockets, ultimately. Now, there's a network card in your computer. And the network card handles connections, but it doesn't just handle one connection. It can handle 64,000 connections. So that means any data that comes into the network card or the network port of your computer has to be handled by some software element. So in other words, how do you communicate? Let's say you have two browsers open. Each one has got its own socket, right? Each one has its own channel of communication. Socket is a channel of communication. Even though they're all going on the same wire, because on the hardware level, it's one wire, but in the software level, we can divide it up into 64,000 channels. So that allows you up to 64,000 simultaneous connections. Of course, they're not really simultaneously. Each time a packet comes in, let's say a piece of information comes in, it will specify, please go to socket number 312. And then I have my software listening on 312, and I know it's for me. If browser 1 is on 312, browser 2 will be 313. So every packet that comes in on that single line of data has in it like an address. Where am I going? Not only which computer in the internet am I going to, which is my computer, but also in that computer, which socket am I going to? Which software channel? So that's why I'm able to have two browsers open, and both of them are talking to different websites. Every time CNN sends me a packet, it says not only go to Nachum's computer, but go to port or socket. It's also called port. 1,000. And then when I ask to go to when my other browser is going some other place, that'll be sent to a different port.
Surely there'll be overlaps. There's no way that every single browser can have its own socket.
No, yeah, it is. Yeah, it is. Because I don't have more than 60. No, every single browser on my computer.
Oh, it's not like standardized.
No. Well, I'll tell you what it is standardized. That's what it says here. Well-known ports. There's such a thing is called well-known ports. For example, you see here. Look at this story. Before I talk about well-known ports, look at this picture. You see this number 161.251.19.8. Those four numbers are the IP address. You ever heard of IP6? You heard of IP6? IP6 is going to have, instead of 4 numbers, I don't know if they still have it, if they have it yet. We've been talking about it for 10 years. But IP6 will, instead of having 4 numbers here, we'll have 6 numbers there. But essentially there's 4 numbers here. And then what's this colon 1625? That 1625 is which port? In other words, this number 161.25.19.8 specifies one computer in the world. Specifies a particular computer. The port number says, on that computer, which port should I go to? Now, Gabby is asking a good question, which is, well, I understand that. If I have Chrome always on 1625, and Internet Explorer is always on something else. So the way it works is like this. All HTTP communication is on port 80. So when I open a browser and I go to CNN, the communication will be on port 80. But that's only the first packet that I send and the first packet that I receive. Immediately there'll be a negotiation. Okay, where should all future communication be? So there's a well-known port. If I want to talk to, if CNN wants to send me something, he's going to send it to 80. But I can tell it now, but don't send to 80 anymore. Once we've established communication, I can say now send it to 1625 or any number I want among less than 64,000. So among those possible ports, I can choose any one I want. And now all future communication is going to be sort of pushed off onto that new number. So now when CNN talks to me, it's not going to send it to port 80, it's going to send it to port 1625. Every packet will be labeled, go to Malcolm's computer at port 1625. But not the first communication. Because otherwise it wouldn't know where to go. It's going to assume that my browser is listening on port 80. But that's just for the first packet. And then and then I respond, CNN, please send me future. I actually, the receiver tells CNN where to send it. So I say, now I want you to send it to some other number. And then CNN will send it to that number. So there's a kind of handshake going on, like communication going on where they establish on what new port the communication will reside. And what's the point of that? The point is, what? Exactly. Now 80 will be open again for the next guy who wants to communicate. Right? I never want to have anybody on 80. That'll be always available for the just that initial communication. And all subsequent will be sort of portioned off. It's like when you go to get your, I'll give you another mashal, when you go to get your COVID vaccination. So there's like a person who meets you and tells you, oh, you go to table 12, go to table 14, go to table. But you don't do but you have to have one point of meeting because otherwise I wouldn't know where to go. I need to have a well-known port. I need to have a place I need to know that I'm going to this door. And then at that door, she can or he can tell me where to go. Turn left, turn right. Go to port, go to table number 1625 and continue communication over there. Dispatch. It's like a dispatch. So that's the idea of well-known ports for services. I just gave you an example of HTTP. So here you just see the web server. This picture this shows what I would say. There's some kind of communication going on port. Oh, you see it says 80. See it says 80 there? You see, when I want to go to CNN, where am I going to go on CNN? I don't know that they want me to be on 1625 or some other random number. I'm always going to go to CNN at port 80. Then CNN is going to tell me, for all future communications, please talk to me at port 312. I'll say, okay. And then, but my first message told CNN, please communicate with me on port 7224. So now our communication is 312, 7224, all back and forth. After that initial thing. So here you see, this picture is not exactly telling the whole story, it's just saying, I'm going to port 80 on him, but he's coming back to me at 1625. That's true. But actually, I may go off of port 80 at some point.
When you're going to let's say going to CNN, if they have one specific place that all of the data requests go to, then how does it not get like crowded even if it's constantly being like
So many. Yeah.
there's lots of well-known things.
Yeah. It's a good question. The answer ultimately is they have many servers. That's the problem. Even with this system, it still was not still not designed for billions of connections.
That's why sometimes it can take a while to load because you have to be like on a queue of like where to be reassigned, or that's not really.
There's many reasons why it can be slow, but it's a lot of points along the path, but I don't know exactly why. No, they should have enough servers. That's why a server will crash. Server will crash, they can't provide service crash, we can't provide service. Let's say you only have one server and 1 million people are trying to come to it. So the port 80 will get, you won't be, your message will go to port 80, but we know there to receive it. There's no queue. I mean, the queue is finite. Even if there's a queue, it's finite. All right, I'm going to skip all this. I'm going to skip this too. This is remote procedure calls. As far as I understand, this is something in Windows, remote procedure, RPC, remote procedure call, where you essentially do an action on a remote server. You say, please run this function on your server. You request it to run a function. Did you do a course in the databases? You're doing now. Are you learning SQL? Not
Yeah,
yet.
so the project,
You will.
the mini project will be SQL.
For the SQL. That's the first I never taught, but I know, I worked with SQL. SQL, you can write little queries. You can write queries to a database to give you information. Now, for example, there's two ways to query an SQL server. One is you log in directly and you do an SQL line, give me from table 12, from table 12, give me line 20, where all, give me row 50, where the value is greater than 100. I'll give you all the data. But a lot of times you don't want to open up your server to such a broad range of commands. Any SQL command, just give it to me and I'll give you the data. Because people could try to put in commands that will ruin your computer, that will hack your computer. So instead, what you do is you do these remote procedure calls. You say, here's a list of possible queries that I'm letting you do on my database. I'll give you 100 queries, and that's it. You want to get some of those informations, choose one of them. So, and therefore you can't do any hacking because you can only do a remote procedure call. You can only say, do this call, do that call, do whatever procedure I have. Let's say the remote procedure. I don't know exactly why it's been put in here. Okay, so here, let's talk about pipes. Pipes is another form of communication. A pipe can be two directional, one directional. Let me explain to you what a pipe is. Well, here's a nice picture of a pipe. A pipe, what would be the basic way of communicating? Most basic way. We talk about shared memory, but shared memory is something you're not so familiar with, so let's talk about a file. The most simple way to communicate between two processes is to have a common file, like a doodling page. Each process can write to that file. I can write to it, you can read to it, you can write to it, I can read from it, and we have communication. Wonderful. Is there any disadvantage in the file? But
But that just makes it hard.
the memory space, what did you say?
To store it, so.
You have to have some memory for it. Well, actually, not memory, what is a better word?
Space. Maybe not hard disk.
Hard disk space. You need to create a space in the hard drive. And essentially, at the end of the communication, when the process is finished, you're going to delete that space. You're going to delete that file. You're not really interested in the file. You're just using the file to communicate.
That's on the drive.
Well, files are always on the drive. That's what a file is. A file is something on the disk drive. So what would we like is a virtual file. A virtual file in memory. And even better, we would like a virtual file in memory which takes up no space unless it's written to. And when it's written to, automatically expands to the size of whatever is written to it. Wouldn't that be wonderful? It would take up no extra, would take up no space on disk. It would take up only the amount of memory necessary. We write to it, and then we read from it. When we read from it, it gets emptied again. And it becomes taking up zero space. It will be the minimum use of resources. We don't have to type, we don't even have to have a disk. We don't have to write to a disk. We don't have to delete from a disk. So that's actually what a pipe is. That is what a pipe is. A pipe is a, metaphorically speaking, a file in memory that takes up no space unless written to. But we call it a pipe because it's like a water pipe that water can go through. In other words, data goes into the pipe, that's our water. Data goes into the pipe, and when somebody drinks from the pipe, then the data is gone. It doesn't hang around.
So when someone breathes from the pipe, basically.
When someone breathes or drinks from, I think it's water.
No, when you're not doing water. Without the water. So when the data
So
goes.
the
into
data
the
is
pipe.
the water.
Okay, yeah.
When the data goes into the pipe kind of is like crushed. It's thin. And as the data gets written into it, the pipe gets longer and longer and longer. Then when the other side somebody reads from it, he drinks the water out of the pipe, and the pipe gets smaller and smaller again. So it's a pipe in the sense that data can flow through it from one process to another.
Is there a way to read from it without it getting smaller, or just not how that works?
No, actually, as far as I know, no. No, when you read from it, the data is lost. Now, there's a one-time, it's like, what is it? Snapchat. Once you see the picture, it's gone. You can't, What?
They have a feature now on WhatsApp.
What's up there?
Yeah, WhatsApp now has it,
I
has
think
a
people
bunch of
can-
things.
People do like they photo, if you have two phones, you can photograph it.
No, you can also do a screenshot.
Do a screenshot, so it's not really, that's. You can also do two phones.
Yeah, but it's easier to do a screenshot.
But how long can you see it?
The screenshot,
No, how long is it on your phone?
if you take a screenshot, it's on your phone for forever.
No, but if you don't take a screenshot,
Oh, it's there for 30 seconds and that's it.
30
Not
seconds.
even.
The 30 seconds is enough to do a screenshot.
10 seconds is enough to do a screenshot,
Yes.
even 5.
But 3 is not.
3 is if you're ready for it.
Anyway, it's kind of like that. It just goes away. You read it and then it's gone. That's why it's a pipe. It's like water. Water in a pipe, once you drink it, it's gone. So here it just talks about you can have like 2-directional, 1-directional. You can have it that both sides can go, can the water go in 2 directions, can it go in 1 direction? But in general, in Unix, what we do is we create a 1-directional pipe where the one side is doing the writing, the other side is doing the reading. And if you want to have 2 directions, you just make 2 pipes. Ordinary pipes are therefore unidirectional. We can talk about this as being a producer and a consumer. The writer, this is going to be useful for when we talk about producer and consumer, just to understand the concept. The writer,
Class.
what?
We have a class in 14 minutes.
So we'll stop now.
Yeah.
But just, no, actually, we finished 3. Name pipes, doesn't matter. But the idea is that the producer is the writer and the consumer is the drinker, the reader. All right, so great, we finished